Okay. Last class, like we discussed about 2D flows, right? And we came to know that in 2D flows you can have a variety of like flows. I mean, different kinds of vector fields and those things. So we saw last class that you can have something like this diagram, okay, which is like this. You can see that it was a saddle. We considered this example over here, right? So we considered this dynamical system, right? This one. What is the question here? So you can see, I gave you one question. So in that, we considered a 2D flow, and in that, the eigenvalues were -3 and 2. That means lambda 1 corresponds to which eigenvalue? Is it stable or unstable? Anyone? Yeah. So lambda 1 corresponds to stable or unstable eigenvalue. That's the question. What do you think? So of course, what is the condition for an equilibrium point to be stable? The real part of the eigenvalue should be less than 0, right? That's what we derived. That's what we did derived yes last class, right? So what we saw in the last class, we discussed in last class, like if these eigenvalues, I mean, let us start from here somewhere. Maybe I have given you this idea, so you should remember about this. So the idea is like if you can see over here, like go on. So equilibrium point is saddle. Like equilibrium point is stable if all the eigenvalues have real part less than 0, right? You agree to this, right? So if you have an equilibrium point, how you will find an equilibrium point? You just set the right hand side to be 0. X dot equal to f of x, set f of x equal to 0. So by solving that, you will get the equilibrium points. Now, how will you know the equilibrium point is stable? If you compute the Jacobian matrix and the Jacobian matrix, you will get the eigenvalues. Now, if you get the eigenvalues and you see all eigenvalues have real part less than 0, then the equilibrium point is stable. Else it is not stable, right? Then you can see it is unstable if all eigenvalues have real part greater than 0. All eigenvalues. Now we have considered either all eigenvalues are less than 0 in real part or all eigenvalues are greater than 0 in real part. Now what happens if you have a mixed number of them? That means some eigenvalues are greater than 0, some eigenvalues are less than 0. Then you get a mixed state. Then you get a mixed state. What does it mean? In some direction it is attracting, and in some direction it is repelling. So it's a mixed behavior. Such kind of mixed behaviors are known as saddle behavior, right? So therefore you can quantify or qualify, you can characterize that equilibrium point as a saddle equilibrium point. So you can see an equilibrium point is saddle if you have mixed type of condition. That means some eigenvalue is less than 0 real part, some eigenvalue are greater than 0 in real part, right? So we saw this example last class where you can see clearly that we had this eigenvalue, this eigendirection, maybe I can mark it in blue, okay? So you can see this eigendirection over here is the stable eigendirection, right? Why? Because you can see along that direction at this point it is attracting. It is attracting. They are converging towards the equilibrium point. Whereas if you see the other direction, whereas if you see the other direction, that is this, then you can clearly see that it is unstable. Why? Because along this direction, it is going away from the equilibrium point at the origin, right? So therefore, there are two kinds of direction. One is stable direction where trajectories or vectors are approaching to the equilibrium point, and there are unstable direction where trajectories are moving away from the equilibrium, right? So therefore, these due to these two direction, you see behavior like this. I mean, let us take one point here. So if you started from here, then you integrate your system, then flow will continue. Why it will continue along this direction? Because you have an equilibrium point along this, the eigenvector direction. So it is approaching like this. Then what it will do, again due to the red direction upwards, it will go like this. right? You understood the idea, right? So now let us take some other case, like along this direction. If you started somewhere from initial condition here, then due to this stable vector, it is coming along this direction. It will come, but along this direction, it is moving out again. So it will go like this, right? Now, what will happen in between these two directions? What will happen in between these two directions? Like you can see that if you start from here, then along this direction it will go, and again it will go till here, and again it will be forced to return along this direction because of the repelling direction, right? So therefore you can generate this diagram. So you can see how in a 2D flow, just because of the mixed kind of eigenvalues, that is real part in is less than 0 in one case, and real part of eigenvalue is greater than 0 in one case. That is here. You can see here real part is less than 0, here real part is greater than 0, right? Because of this phenomena, like we see this kind of a flow, and different regions of the phase space have different movements, right? You can see here the movement is quite interesting. It goes like this. Here the movement like this. Here the movement is quite interesting like this. But here the movement is even more interesting, like it will go like this. Different flows. Okay, different flows. So you can see how it can be. Okay, I hope you might have seen this kind of flow behavior or in ponds or in river flows, right? Where you put one small boat, paper boat, right? You try to put and you see where it goes, right? So you might have seen that they might follow one trajectory, but in some case you might see that they circulate. They circulate in spirals, right? So they do many things. So those behaviors are also shown here. That's the aim of dynamical systems, right? Okay. Now what we will do is let us go to another case. Okay, let us go to another case. Maybe we can start with another diagram. So yeah, this will be interesting. So let us see. Yeah. Let us take this case, right? Let us take this case. Like you have a 2D flow. Okay, you have a 2D flow. What does the 2D flow look like? The 2D flow is this. X dot is say 3x plus y, and y dot is 3y. Suppose you have this diagram, this flow here, 2D flow. Now my question to you is how the 2D flow, draw the phase portrait. My question to you is draw the phase portrait. So what does phase portrait mean? Phase portrait mean is to draw on the plane of x and y variables how the flow will occur if you start from different initial conditions, right? Okay, so my question is this. So what is our first step? Our first step is to convert this 2D flow into the form, say x dot equals to ax, right? X dot equal to x, where capital X is nothing but x and y, right? Agree? Yes, if you do that, what will be, can you tell me what will be A? A will be 3, 1, 0, 3, right? You can write x, y here. Or if you prefer, like x dot, y dot is equals to 3, 1, 0, 3, x, y, right? Fine? Okay. Okay. So can you tell me the eigenvalues for this? Now all depends on this eigenvalue, right? All depends, the whole flow depends on this eigenvalue. Now my question to you is, what are the eigenvalues of this matrix? What are the eigenvalues? So the eigenvalues are only one eigenvalue, isn't it? Why? Because lambda 1 plus lambda 2 is nothing but 3 plus 3, that is 6, right? And lambda 1 times lambda 2 is 3 times 3 minus 1 times 0, that is 9. So therefore from this you can see that both lambda 1 and lambda 2 are 3. Okay, both lambda 1 and lambda 2 are 3. Okay, that means it's a repeating eigenvalue. It's a repeating eigenvalue. Eigenvalue multiplicity is 2. Okay, same eigenvalue is repeating 2 times. Now that you have got the eigenvalue, what is the corresponding eigenvector? So what is the corresponding eigenvector? So the corresponding eigenvector is say v1 or v is equal to what? Can you find? Can you find? So what you have to do? You know ax equals to lambda x. So a minus lambda I times x is 0. So you have to find x is what? X is what? So that a minus lambda I x equal to 0 is satisfied. That is the question. Okay. Now can you tell me the vector? Yes. Any ideas? What is the eigenvalue vector? Hmm? Anyone? What is the eigenvector? Yes, x 1 0 1 0, right? Eigenvector is 1 0. Fine. So what can we draw the phase portrait? Can we draw the phase portrait now? Let us draw the phase portrait. So what we will have? We will have x and y. Fine. Now what does it tell? That now tell me the eigenvalue you got lambda 1 and lambda 2 equal to 3. Are these stable eigenvalue or unstable eigenvalue? They represent to the stable eigenvalue or a unstable eigenvalue. What is the real part? Real part of eigenvalue is 3. That is greater than 0. So is it stable or unstable? Unstable, right? So what does it mean? So corresponding to eigenvalue 3, this eigen direction 1 0 is unstable. Okay. Where 1 0 lies? Where eigenvector 1 0 lies? X-axis, right? And any multiple is also an eigenvector. Any multiple of v equal to 1 0 is also an eigenvector. What does it mean? It means full x-axis is the eigenvector, right? So it means that this is the direction over here, right? This is the direction over here. It is totally unstable. Where is the fixed point? You can see origin is the fixed point, right? For fixed point, you set x dot equal to 0. That means 3x plus y equal to 0 and 3y equals to 0. So from here, you can conclude that both fixed points are at the origin. These are the equilibrium points, isn't it? These are the equilibrium points. Fine. Agree? So this equilibrium point is unstable. This equilibrium point is unstable. Okay, that means along this direction, your vectors will diverge. I mean, they will go away, right? You got the idea. This is the study so far you have made. Okay, understood. Fine. Now my question is, what about other directions? What about other directions? So let us say you can easily see, I mean, just make observations clear. that you have this condition y dot equal to 3y, y dot equals to 3y, what will happen? If y dot equals to 3y, then how y will change? Exponentially. Do you remember how to solve y dot equal to 3y? How to solve y dot equal to 3y? Yes, anyone? This is class 12th stuff. How you do? Some constant c e to the power 3t. Y equals to some constant c e to the power 3t. Right? So what is c? What is c? Y equals to c e to the power 3t I wrote. Now what is c? That's the question I am asking. Now at time t equal to 0, the point you start from is nothing but the initial condition. You need initial conditions to start. So that is at t equal to 0, this is y of t. So y of 0 is nothing but c e to the power 3 times 0. So y of 0 is nothing but c. So you can write this equation as y of t is nothing but the initial condition y of 0 e to the power 3t. So as time progresses, it exponentially diverge. It will exponentially diverge, right? Exponentially. So how, suppose you started from this point. Suppose you started from this point, what will happen? Can you tell what will happen? It will diverge exponentially. It will diverge exponentially. So y diverges exponentially. So it will go like this, isn't it? Is it fine? Can we take some other points? If you are here, it is going something like this, right? I mean, it is going towards infinity, right? I mean increasing. Yes. Can we take some other points? Can we take some other points? What happened to this? Here, it will go like this. Here, fine. Y is increasing exponentially. Y is increasing exponentially, right? Y is increasing exponentially. So if you choose a negative direction, it will increase in the negative way, but go towards minus infinity. If you start from here, it is going like this. Here also it will go like this. Here also it will go like this. So you are able to see, you are getting the effect. You're getting the effect. You're getting the effect. How these different initial, what are these points? What are these special points? These special points are nothing but the initial conditions. These special points are nothing but the initial conditions you started with. Agree? You understood how this diagram is working, right? But along this direction, it just goes outwards. Okay. There, y doesn't have any value because that is x direction. Y is 0. Y is 0, right? Okay, fine. If y is 0, x dot equal to 3x. If y equal to 0, x dot equal to 3x. Yes. So that also will diverge exponentially. Right? So you can see this is the phase portrait. Okay. This is the phase portrait for this system. I'm trying to give you ideas. What kind of different flow behavior can be seen in 2D flows. So we saw saddle behavior. We saw this exponentially going outward behavior, right? You understood this. Now let us see another case. Let us take another case. Okay. Okay, this one will be another one. Can be interesting. Like simple case, x dot equals to y and y dot equals to minus x. Okay. This is another 2D flow. And my question is, draw the phase portrait. How this phase portrait looks. Okay. Hmm. Yes. But the first step? the first step is to write x dot equals to ax, right? So then what is a? A is nothing but 0, 1, minus 1, 0, right? So what are the eigenvalues here? What are the eigenvalues? But you don't need eigenvalues at all. I mean, you can see. Can you do some other things like maybe compute eigenvalues? That will be better. So what are the eigenvalues? Are eigenvalues real or eigenvalues are complex? Are eigenvalues real or eigenvalue complex? Huh? Complex. Hmm? Complex. Right? What are the complex eigenvalues? Hmm? What is that? I. Hmm. Complex conjugate. If eigenvalues are complex, they will be complex conjugate, right? They will be complex conjugate, no? Hmm? What to do next? Next step is, what is the next step? Hmm? Shall I give this as assignment? Hmm? Assignment. Third assignment. Third assignment. Okay. This will be the third assignment. Okay. So how you will get to this face portrait? How this face portrait looks like? So the face portrait is quite interesting in this case. Okay, I will tell you the answer how it looks. So the face portrait you will have is something very interesting. Like they will be closed curves. Okay, they will be closed curves. The each represents a starting condition. Each represents a starting condition. Okay, so this is x, this is y, and this is the face portrait. So why this is the case? Can you work it out? That's the assignment. Okay, so this is the face portrait of the 2D flow. This is the face portrait of this 2D flow. Okay. Fine. Okay.